Hello, and thanks for joining me today. My name is Will Cunningham, and I'm the head of high performance computing at Agnostic. Today, I'll be talking to you about Covalent, our open source orchestration platform for distributed and heterogeneous computing. Let's get started. Cutting edge problems in computational science are often very hard to understand, let alone solve numerically. Researchers in this domain often employ high performance computing, or HPC, tools to simulate large, complex systems while iterating over dozens of models and input parameters. Over the course of this exploratory process, a proliferation of data, parameters, and software versions can leave these researchers with a monumental task in organizing and publishing their work, even when best practices are employed. As the demand for HPC resources has increased over the past several decades, a complex landscape of powerful technologies has emerged. Today, someone entering this space is faced with an abundance of options when it comes to how and where they run their workloads. Users are presented with a multitude of types of devices, including many core CPUs, GPUs and TPUs, FPGAs and ASICs, and now even quantum and quantum-inspired devices. If this weren't already enough choice, users also need to decide how they access these devices. Organizations already doing HPC most often already touch several of these components in a hybrid configuration. There are several market trends which promote this degree of complexity in HPC. First, as we can see in the image on the right of this slide, traditional on-premises supercomputers have begun scaling at a slower rate for a little over a decade now. As upgrades deliver less relative return than in the past, it has become increasingly common for users to have access to multiple supercomputers, and it is likewise common for providers to join together to deliver federated access where identity and data is shared across previously distinct systems. Many providers are also beginning to consider options for cloud bursting, where jobs can be offloaded to cloud-based compute resources during periods of high demand. These patterns together paint a clear picture for a new type of HPC emerging: high-performance distributed computing. As quantum computers enter the market, their user base is immediately exposed to heterogeneous computing. Consider the toy quantum machine learning experiment depicted in this diagram. Pre- and post-processing is most often done on a user's local workstation, while training steps are offloaded to GPUs and quantum processors, or QPUs. Already, this involves three types of compute paradigms. To make matters more complicated, with GPUs and QPUs in high demand, it is common for steps in a job to wait in queue for minutes or hours, leaving valuable clock cycles unused. In a small experiment, this may be acceptable, but at scale, it becomes untenable. To address these complexities, we've built Covalent, an open source workflow orchestration platform for heterogeneous and distributed computing. Covalent acts as a single entry point to the broader landscape of compute so that the growing complexity of hardware and compute platforms is decoupled from end user applications. Covalent provides a rich browser-based user interface which allows users to monitor experiments in real time, track data as it moves across the landscape, trace errors back to their source without scouring otherwise distributed logs, and more effectively communicate where time and money is being spent across a project. Covalent doesn't just support heterogeneous hardware, it also supports heterogeneous software. While the orchestration is done in Python, workflow tasks can be written in other languages such as C++ and Bash. This allows users to deploy any software to any compute backend, all while leveraging Covalent's powerful orchestration engine to keep track of metadata. As opposed to other workflow tools, which use workflow templates as first-class citizens, Covalent is centered around workflow dispatches, or invocations. This promotes rapid iteration of experimental workflows as one navigates through the research phase of a computational project. As workflows pass through the Covalent server, all sorts of metadata is collected and stored with the result. Everything from benchmarking data to checkpointed partial results to software and files used during runtime. This information is then displayed in the user interface so that users can easily click a button and know everything about the dispatch visually. This allows users to focus on high-level communication and ideation without spending too much time on note-taking. Let's take a closer look at some of the core features Covalent provides. First, real-time monitoring allows users to gain immediate insights and feedback about how an experiment is progressing. As tasks complete, users can inspect checkpointed results and immediately copy them back to a notebook for further analysis without waiting for the full workflow to complete. Second, Covalent's robust collection of metadata facilitates the greatest degree of reproducibility which can be attained. If users need to share a workflow with a colleague, they can be sure it will run exactly as it ran earlier, no matter how much time has passed. Further, when onboarding new team members, software reproducibility minimizes the time it takes for them to get up to speed working on a new code base. Third, Covalent now supports stopping and restarting workflows using the cancel and redispatch features. This takes a huge weight off users running workflows at scale. When a single task fails, there is no need to rerun all previously successful tasks thanks to caching capabilities. Finally, Covalent now supports both batch as well as stream processing. Both event-based and time-based triggers allow workflows to run in response to external events, allowing users to integrate Covalent into dynamic tech stacks. Let's now take a look at how Covalent works. Covalent uses a client-server architecture. A Pythonic SDK is used to construct workflows and to interact with the Covalent server. The Covalent server runs on the user's local workstation out of the box, but it can also be deployed in a variety of other methods, as I'll mention later. The server contains a dispatch service, which manages workflows and tasks, as well as a user interface, which provides a visual representation of everything going on in the dispatcher. The image on the right shows a representative snapshot of the user interface. Covalent connects to compute backends using a plugin system. This allows users to customize their particular deployment of Covalent, allowing them to hook up to the right compute backends while keeping the deployment lean and efficient. Let's now discuss some of the concepts a user needs to know when getting started with Covalent. The first major concept is that of the electron, or workflow task, which is a regular Python function with an electron decorator on top. This decorator transforms the function into a workflow task with all sorts of metadata about the task both before and after invocation. The second concept is that of the lattice, or workflow definition, again a Python function, this time with the lattice decorator on top. This function serves to define the data dependencies between tasks so that the Covalent server can properly pipe data across distributed compute backends. The third concept is that of the dispatch. This is simply an asynchronous deployment of a workflow to the Covalent server so that users need not keep a Python kernel alive while waiting for a result. As I previously mentioned, Covalent requires only minimal changes to existing code bases to transform them into workflows. On the right-hand side, you can see functions are decorated with some of the supported executors. One submits a task to AWS Batch, the second submits a task to a cluster managed by Slurm, while a third submits a hybrid quantum task to IBM's Qiskit runtime service. While other parameters describing connection details are stored in the Covalent configuration file, users are left with an extremely simple interface to offload jobs while only thinking about high-level resource requirements. Even better, once connections are set up, it becomes very easy to fine-tune resource requirements, swap executors, and reroute tasks depending on availability and cost constraints. Let's take a closer look at Covalent's user interface. A workflow is displayed graphically in the center, where graph nodes represent workflow tasks. Each node displays status information describing the current state of the corresponding task. On the left-hand navbar, we see all of the workflow-level metadata, while clicking on individual tasks will bring up task-level metadata on the right-hand navbar. The source code and workflow inputs are also included in all dispatches so that Covalent also acts as a form of software version control. Covalent's dispatch service is highly efficient, allowing workflows with thousands of tasks, even on machines with moderate resources. The key to performant orchestration at scale is to leverage the plugin system and to keep large data on remote systems. With only metadata passing through Covalent, the system remains performant even under high load. Now that we've covered the basics, let's dig into some of Covalent's best features. Covalent allows users to nest workflows within each other using a concept called sublattices. Sublattices are workflows which are tasks within larger workflows, and their structure is determined at runtime rather than when the parent workflow is initially sent to the Covalent server. This facilitates a few useful patterns. Users can construct workflows which use conditional logic, such as branching and looping. Users can also structure dynamic workflows to support real-time cloud bursting. Downstream tasks are offloaded to whichever hardware has the shortest queue times or lowest costs. Likewise, users can build workflows which use dynamic parallelism, where the degree of parallelism is determined at runtime according to the available compute resources and algorithmic constraints. With dynamic workflows, users have a much greater degree of flexibility than when using other workflow tools. Another massively powerful feature of Covalent lies in its Executor plugins. Modularity is at the heart of Covalent's design. By leveraging a plugin system, it becomes easy to add and modify integrations to a variety of compute backends without introducing bloat through third-party packages. Covalent's plugins can be grouped into three categories. The Kubernetes and Slurm plugins allow users to connect to popular orchestrators for on-premises, general, and high-performance compute resources. Each includes features specific to their respective orchestrators. The Kubernetes plugin integrates with managed Kubernetes services, while the Slurm plugin plays well with environment modules, MPI, and Conda environments. The AWS, Azure, and GCP Batch plugins support cloud-based batch processing on a nearly limitless range of compute options worldwide. These plugins work well for users who are already cloud customers. The Amazon Bracket and IBM Qiskit runtime plugins allow users to offload variational quantum algorithms to some of the emerging hybrid quantum services. On top of all these great options, we also provide a custom Executor plugin template so that users can easily create their own custom plugins to other compute backends by filling in about 50 to 100 lines of code. This image shows an example of what a user can achieve using these plugins together. Here we see a quantum circuit being simulated on 4 different compute backends: Amazon Bracket Hybrid Jobs, Microsoft Azure Batch, Google Batch, and Dask. This type of setup is optimal for comparing hardware performance in HPC and quantum computing experiments. Finally, let's come back to discuss Covalent's deployment options. New users will most often want to install Covalent locally on their workstation using either pip or conda. However, larger workflows may benefit from a dedicated resource for the Covalent server, either on the cloud or on another computer in a local network. Covalent can easily be run as a separate SDK and server Docker containers using pre-built images provided by the Covalent team. Covalent can likewise be installed as a systemd service, which can be useful for long-running deployments on virtual machines. On the cloud, users may prefer to launch Covalent Server using a cloud console. For instance, on AWS, users can deploy a Covalent Server AMI with just a few clicks. Finally, more sophisticated users may choose to customize their deployments even further using Terraform and/or Ansible. All of these options are made available in order to meet the needs of a diverse user base. There are, of course, many more features that I haven't had time to cover in this video. You can get started today by checking out our page on GitHub, joining our Slack community, or subscribing to our newsletter on our website, covalent.xyz. Covalent is open source and fully customizable, and we encourage community contributors to participate in its development. If you like what we're doing, drop us a star on GitHub or connect with us to let us know how you're using Covalent to accelerate your work. Thanks for listening, and have a nice day.